Now we're on air. Yeah. All right. Thanks, everybody. I think we all met this morning, and those who didn't meet this morning, I know already. So I'm Constantine, University of Colorado. I'm going to be answering your favorites of my questions. This is for the British people. Oh, no. Okay, and before I do that, also this room's like a little bit echoey, and I have a tendency to project, so this is going to keep me from projecting, which maybe that's good for everybody. Cambridge Beer Festival today, 4 pounds to get in, 5 p.m. plus Epsilon is, well, it starts at 5 p.m., so I figured 5 p.m. plus Epsilon, walk over there, grab a drink, and maybe this discussion will be so spirited we just have to go get a drink afterwards. That's what I'm hoping for. As you may know, I put this picture with a piece of paper with a bunch of problems up on my door, and I asked you all to vote on it. So here's the results of the voting. I think there's a relatively strong signal there. So I'm going to go with problems 6, 7, and 8 from these. And what did those turn out to be? That was asking about connections between regression and approximation, Gaussian processes and RBFs, designs, as in design of experiments in quadrature, and then what is noise in a computational model, and how do active subspaces relate to a whole host of other things. But we're going to start here, because we only have so much time. Several of you are probably more equipped to answer this question about design versus quadrature, and I sort of hope that we could start by talking about regression versus approximation, and then in later conversations after the seminar we can sort of translate that into things that are sort of Gaussian processes and RBFs related. The next slide, the next slide was actually supposed to be at the very end, practical suggestions, but I figured this first practical suggestion was something that I would put at the very front, as soon as we started talking about questions, which is everyone, civilized conversation and argumentation, please. So certainly when we talk across disciplinary lines, there is a temptation, or when we look at things across disciplinary lines, there's a temptation for all of us to be reductionist, to say, I work on this thing and I see this other thing over there, and oh, that's just this. And I would strongly encourage you to not use that word just. Say, oh, that's this thing, how do these relate? And not to immediately jump to, that's just this thing or that thing. And think of it as an analogy, and then you want to uncover what the real relationship is within the analogy. I hope that we get to the point of sort of brainstorming, and if you've ever done brainstorming sessions, you know the rule is there are no bad ideas in brainstorming, right? But we have a tendency as academics to be like, no, that's not right. I know that's not right. But and then have you ever done improv, like community improv kind of? Has anyone ever done improv? You know what it is. Okay, there's a rule in improv, I've done it like once, called yes and, which is if you're in an improv scene and someone says something like, we're going to go on a trip, you don't say, no, we're not going on a trip, you say, yes, and we're going to go to Jamaica, or something like that. So yes and is a way to help with the conversation be civilized. Don't be afraid to say, I don't understand. I think, I have seen so many talks where everyone's quiet through all the talk, and then you leave, and you hear whispers like, I didn't know what he was talking about, right? Like that's what we do. So I would encourage you to not do that, that if you don't understand something, say it. And then hopefully, once we get through those sort of like social and cultural things, we can flesh out precise mathematical ideas with precise notation, have theoretical kinds of comparisons, and also transparent numerical experiments so that we can really like have a precise comparisons of things. And then lastly, just be nice. Don't be an asshole. I feel like this should be our one rule in our community. I mean, I'm as guilty of it as anyone else is, of being an asshole at times, but I really try not to. And I want us to try to give others the benefit of the doubt, not to take arguments personally, and to drink beer together. Okay. So with that, here's a trigger warning. The universities, we often are worried about specific words that can trigger things in people. So I think these are trigger words for our interdisciplinary community. Data, model, noise, parameter, error, uncertainty, overfit. These kinds of things, if you're a statistician, you have grown up, you have been trained with a particular way of thinking about these words and what they mean precisely. I think in general, the mathematicians will tend to use these words a bit more loosely. I can give you an example from UNQ that was in Lausanne. I was texting with a colleague who was a statistician, and we were listening to a speaker that was a prominent applied mathematician, and the colleague texts me and says, I can't listen to this person. This person doesn't even know the difference between parameter and variable. I was like, well, mathematician, parameter, variable, what's the big deal? But this statistician was very concerned about the precise notion of a parameter. Okay, so that's just a warning that these are words that mean different things in different contexts. I think I'm comfortable saying everyone in this room will be comfortable sort of reserving judgment when using these kinds of words if someone uses them potentially incorrectly, including me. So here is a selected bibliography. These are papers that sort of I've gone back to or that I started with in my journey from UQ through statistics and modeling. I would not actually recommend this precise order of the papers, but I just wanted to give you a couple references to tell you sort of where I'm coming from. So the Gahneman Spanos book, Stochastic Finite Element, and Dogbin, Hughes, and George Karniadakis' paper, We Now Ask Polynomial Chaos. These are the oft-cited papers for polynomial chaos methods. I think even if you ask Dogbin now, he'd say, yeah, I really wish I would have written that thing differently. I never read these anymore, but just to tell you that sort of this is where I started when I was in grad school reading these things. And then similarly with sparse grid kind of stochastic collocation methods from Fabio and Raoul and Clayton. But then I found out that, orthogonal polynomials have been around for hundreds of years. And this work was presented to me as a new grad student as this new methodology for uncertainty quantification, and it was like, orthogonal polynomials? They've been around for a long, long time. So then, after sort of understanding this literature, I found Jim Kohler and Art Owen's paper, Computer Experiments, and Don Jones, A Taxonomy of Global Optimization Methods. Computer experiments, I think most of us here are familiar with, and then global optimization methods using response surfaces. And I was like, whoa, a lot of the things that they talk about up here are explained much more simply in here. And also, this paper from '96 used the phrase quantify uncertainty, and I was like, I thought that was invented in 2000. I was learning things. And then finally, as I've sort of gotten into more of the statistical literature and the statistics methods, Dennis Cook has been a very helpful person to communicate with, and his book, Regression Graphics, has really shaped the way that I think about regression. And so related to that, I'm going to begin contrasting these two perspectives on what to do with data. Okay, so here's Weisberg's Applied Linear Regression. This was a linear regression textbook in my graduate linear models class. And then Rivlin's an introduction to the approximation of functions. Both of these are sort of introductory graduate textbooks or even late undergraduate kind of textbooks. But although they look like they deal with very similar things, they come from very, very different perspectives. And so that's what I'm going to try to detail first. And I think that difference in perspectives translates to the difference in these two perspectives. Gaussian processes from machine learning by Rasmussen, who's down the road somewhere, right? He's around here. And then Holger Wendland scattered data approximation, which is about radial basis function approximation, and reproducing kernel Hilbert spaces, and the error analysis that goes along with that. So I hope that we eventually can get to having discussions about this. It won't happen in this hour. So I'm going to contrast regression versus approximation. Now, I got really excited when I mentioned to John this morning that I was like, yeah, I'm talking about regression versus approximation. He said, aren't those the same thing? How many of you think they're the same thing?
One is approximation. Regression is a form of approximation.
Oh, that's interesting. I wonder if you'll have the same viewpoint when I'm finished. I very much appreciate you saying that. Okay, let's start out with regression, and we're going to keep everything. Let's see if I missed any notes here. I've got some. One thing that I did want to say here is that this is my perspective on this comparison. There are certainly other perspectives on this comparison. This is meant to start a conversation rather than end the conversation. Okay, so I tried to make it as simple as possible, and specifically restricting to one-dimensional approximation or regression or univariate. Both of these are semester-long courses, and I'm going to cover them both in 15 minutes. And of course, the danger in such an overview, in such an oversimplification, is making both sides upset. So I hope to not make everybody upset in the room. And ultimately, I'm going to say that I think some of us should write a report, somebody, and I'd be happy to help write a review paper comparing these things. Okay, so back to this. So the idea behind regression is that you're given independent, identically distributed samples, input and output, or in regression they'll call it predictor and response, from some unknown joint density on the predictor and the responses. So I've drawn it up here to pretend that I know what it is, but really in regression you're given these things and you assume that it comes from this along with the independence assumption. And now the goal is to statistically characterize the random variable, that is the conditional random variable response given predictors. Okay? And for example, to statistically characterize, you might want to compute moments, first and second moment. The expectation of y given x, the variance of y given x. Now, in order to do this, the regression procedure begins by modeling the relationship between the response and the predictors. And so you might say that this model right here, say for example a polynomial that also depends on theta, the polynomial coefficients, is your model for the expectation of y given x. And then this other thing here is modeled as a zero mean random variable that is independent of x, representing the noise. So what that represents is that for a fixed value of x, there's still some spread in y, right? That really is a random variable. That's where that randomness is coming from. So you can think of it as a decomposition of mean plus fluctuation, which we often do in fluid dynamics. Once you set up this model, now the process is to fit these parameters from this given data. And so, for example, I think everybody knows how to start with a maximum likelihood problem and ultimately derive at a least squares problem. So I'm showing here a least squares problem where theta hat is my estimator of the true value of theta, which is just the minimizer of my squared loss function for my yi and my xi there. Now, once I have fit this parameter with theta, now I can predict for some new x star that's not in my set. I can evaluate this polynomial model at that x star and the fitted parameters, which I'll call p hat for simplification, and then that gives me some curve through this data. And now the statisticians will say that quantifying uncertainty might include, for one particular value of the predictor, this x star, I not only get a prediction, but I get some measure of uncertainty, and that conditional variance is some kind of formula that comes from this data. Regression. All of you are like, yeah, fine. We got regression. Regression in 1D. Okay, so now let's look at approximation. How is approximation different? Approximation begins with a different problem. Approximation generally begins with a very large class of functions, and then some much smaller class of approximation functions. Okay, so for example, you can think of the space of continuous functions as your big class of functions, and maybe polynomials of some finite degree as your smaller class. Now from this, the approximation theorist is going to ask first, does a unique best approximation exist? Meaning, from my small class of functions, can I minimize the difference over all of my small class of functions for some function coming from my big class? And does this thing exist for any f from this big class? Now you might ask, how does this best error behave as a function of, for example, the polynomial degree? So if p star is my minimizer, it depends on this polynomial degree. I want to see what happens to this best error as the n increases. All of this is just analysis. Now the question is, if you actually want to be constructive about it, then the question is, can we construct an approximation? So given an f, can I actually compute some p hat? And producing some algorithm for that, and then studying the complexity of that algorithm. And can we analyze its error? In particular, what we want to show is that somehow this thing that we can compute, if we look at its error, it's somehow related to this best approximation error, potentially bounded by best approximation error times some constant that's independent of that parameter that changes. So these are the ideas behind approximation. Now we go back to the case where we had data, and the problem setup is different. Okay? So as opposed to given xi, yi, we are given a function, and we're given some known density. Now, in the approximation literature, this is often not emphasized. It's more emphasized in the UQ literature because this thing represents some notion of uncertainty on the input parameters. But even in all the approximation literature, this is often part of some norm, which we'll get to in a second. Now, the goal is once we're given this function and this known density, find some p hat such that this error is sufficiently small. And I'm going to give you a constructive way to do this. The constructive way to do this is to choose xi. It was not given to me. It was not sampled necessarily from, it could be sampled from this density as independent samples, but it could be a quadrature rule. It could be some kind of rule associated with this density, but I choose these xi's. For each of these xi's, I query my function, or I evaluate yi as f of xi, and now I can do any kind of fitting procedure that I want using the xi's and yi's, and again, I'm just showing the least simple discrete least squares kind of approximation. Now, something that I emphasize to my class is that although this discrete least squares problem is the same as the least squares problem derived from the maximum likelihood, they come from different places. They have different interpretations. Okay? So this is this point. So although there are certain conditions under which this problem is exactly the same as this problem, and the resulting fitted curve given the same data is exactly the same, these have very different stories associated with them. The data have very different stories associated with them. So the story behind the data and the fitted curve is different. The question is, does it matter? And I'm going to argue that yes, it does matter. It matters for two very specific points, which are understanding convergence and understanding error. So, regression versus approximation, what is error? So if we think about the story of where that data came from the regression side, and the story of where that data came from the constructive approximation side. Now, when I think about error for regression, the way that a statistician or regression analyst is going to quantify uncertainty in the regression prediction is to build some kind of a confidence interval, potentially using a plug-in estimate of the standard error, which is computed from the data. So for example, the regression prediction plus or minus 2 times some kind of standard error. The approximation error, and that's related to their assumption on this distribution that gave them the data. The approximation error, in contrast, is one number that's just the difference between the fitted curve and the true value of the function. Now, this is not especially useful because it depends on x, so typically what they'll do is use some kind of norm, like a L2 norm, which would be the integrated mean squared error, root mean squared error, against the given density function, or more commonly in approximation is to use some kind of uniform norm to take the supremum overall of the error over all of the x's. Okay, now the thing that's interesting is that in regression, this is computable, at least in the sense that you can estimate it from the data. You can plug in a plug-in estimate of the standard error and actually compute this confidence interval. This is typically not computable without evaluating the function again. And certainly computing either of these norms is typically not computable because this is an integral, this is an optimization problem, and solving these exactly is not possible. In certain, we can estimate it, but if you don't have a good idea of what f is, then you have to estimate this thing with a quadrature rule, or you have to estimate this with an optimization method. You're not necessarily getting exactly the same thing, or the exact numbers here. But what I think is interesting is that this, in some sense, is more practical because it's computable. However, the thing that you are estimating is not the same thing as the error. The stories that give rise to these pictures are very different, which means this number is very different from this number in its interpretation. All right, so what does convergence mean in regression versus approximation? Again, we think about the stories of where our data came from. So in regression, from a frequentist perspective, as the data increases, you get something called root n consistency, and this is what they mean by convergence, which is that the data-dependent random estimate of theta converges true, the true value of theta, and consequently the data-dependent random estimate of p hat converges to p in distribution as the data increases, with a rate that is 1 over square root number of data points. So that means that if I have this much data, I get this model, and then I draw more data and I fit it again, I start to get a different model. You'd actually see what happens if I kept increasing the number of data points. Eventually, it would end up being a line, even though my polynomial approximation here is second degree, is quadratic. In contrast, the approximation error is treated like this. As the approximation class grows, meaning the degree of polynomial increases, then this error, the norm of the difference between my approximation and the true function, goes to 0. So if I start with an initial set of data and I fit my curve, And then with more data, I can fit a higher degree polynomial. And now this blue curve will start to converge to the story as I have to increase the number of data with some rate related to the degree, with the way I want to increase my polynomial order, such that this happens. The rate at which this goes to 0 is dependent on several properties of f. It's potentially dependent on higher order derivatives. Maybe higher order derivatives that you can't compute evaluated at places that you don't know. But that's what the analysis says through Taylor. The size of the region of analyticity, and related to that also the Chebyshev coefficients of this function f for things that are analytic. Yeah. Okay, so here's the real question for, are there any questions at this point? Everybody's clear?
So,
Yeah.
so in terms of the approximation, so
Yeah.
it's not computable, but one needs to do something about it. So what?
Yeah, so this type of analysis is asymptotic. And so I would say often what we do in practice would be to estimate the Chebyshev coefficients with a fast Fourier transform and look at their decay and then say that the L2 error is related to sort of something close to the last Chebyshev coefficient.
I'm talking about a priori results here, right? It depends on the approximation task and your quantity of interest, right?
If the approximation task is L2 approximation, right? And if the output is a scalar, and if my function is a univariate function, then one a posteriori way that I would estimate the error is to estimate the Chebyshev coefficients, and then look at the magnitude of the last coefficient.
We've had long discussions associated with this and sort of a priori versus uncomputable error bounds versus things that might error estimates that might be computable.
Yeah, I think of these as computable error estimates, if you can do the Fourier transform.
Let's say if you take Wendland, for example, so if you have scattered data and you fit this, what does it do? The type of function is using radial basis functions. Right?
Okay.
Right? Let's say an example. You approximate, and then you're left with an approximation of the error that you come up with in a way that's through asymptotics or...
Yes.
But do you believe this error? This is the issue.
And this is also asymptotics.
This is also
Yeah, and the analysis of this is asymptotics, because actually what you want to see is like how quickly do these Chebyshev coefficients decay, and they depend on things that aren't computable necessarily. But this is the asymptotics. Although error in this case may be computable, it's just not the same thing, right? Mathematically, they're just different things.
So is the community in applied mathematics dissatisfied with this problem? Are you
I think
interested in this problem?
Yes.
In applied math?
But it depends who you talk to.
Error estimation is a huge branch of applied mathematics.
Yeah.
Huge. Decades of research.
So concretely, when you have scattered data and you fit whatever model, or maybe I should not say that, approximation of your function. Nowadays, there are some communities within the applied math community that sub-communities that fit different styles of error.
Yes. Yeah.
It very much depends on what is the approximation task
Yes.
and what is the quantity of interest. If
Oh,
you go to MATLAB, for instance, you can use a black box tool to estimate an integral, or a black box tool to estimate the solution of a differential equation. And they're all adaptive methods, and they're all driven by error estimates. And it's not. There's a whole range of techniques, ranging from
Yes.
ad hoc to things that are computationally very desirable, but don't come with any underpinning analysis, right through to the more sophisticated things, which do come with underpinning analysis. But it's very fair to say that the more rigorous you can, to be very rigorous, you need to exploit more from the problem. So there's a big difference between doing things in a black box setting.
Although rigorous is one of those words that I think that I want to be careful about,
Okay.
right? Because rigorous, in my experience, has been used as a word with implied authority and power.
No, what I mean is either having analysis for me, it's like the difference between having something that's computationally convenient and can be done, but we can't necessarily prove any kind of relationship between that and the real thing you're using it to estimate, versus something where you do have a bit of theory or a bit of analysis to link the two things.
Yeah, which gets to one of my practical suggestions that I'll just skip to the end to, which would be, here's something that we can practically compute. given the data. It'd be really interesting to come up with a relationship between this bar and this bar in some kind of analysis.
And nobody's looking at it.
I believe, so I have seen some of that in the radial basis function literature.
Aretha.
Aretha.
Oh no, I was just thinking, so a relationship between those two red lines that you just pointed out would be difficult, as you said, they're quite different problems. So for
Yes.
example, on the left-hand side, for a fixed value of x, you could have multiple values of y,
Right.
Whereas on the right-hand side, you couldn't. So
Right.
I don't know if there is a clear relationship between those two things.
I know that I have seen such things in the radial basis
Oh,
function
there
literature.
has been, okay.
Yeah.
So it's-
But here, this is really the question for these 6 months, right? Which one of these is a computer simulation? Right? Is it regression or is it approximation? Which one's more appropriate? And in my mind, the answer to this question hinges on how do we think of error in a computer experiment. Yeah.
But isn't the difference between the two is that in approximation you assume that you can always evaluate the function exactly, whereas in regression you don't. That's the only difference, right? It's just two different scenarios.
So I don't know if it's, I wouldn't say that it's the only difference. I would say that the entire setup, the entire story about the assumptions about where these black dots come from is different.
Can you not set up the problem on the left? So given a particular setup of the problem on the right, could you not just pose a particular likelihood and a particular error distribution such that the problem on the left would happen to?
So yeah, I mean,
Solution
if you look at regression from this spot, maybe you say this has that this is mean zero and no variance.
Yeah.
But then this is not a density. It's a more general distribution, and I don't know how to set up a maximum likelihood problem where this is some kind of where this is not a density.
Just go back to your slide with the two pictures alongside with the estimate and yep, that's the one, yeah.
Okay.
So, in sort of regression settings, are you thinking, or do you sometimes think of the problem as it's that blue line that you're trying to uncover, or do you sometimes think that the problem is it's actually the joint distribution of x and y that you're trying to estimate?
Right. I typically think of it as statistically characterizing the conditional random variable. So the blue line would be the approximation of the conditional mean, and then your quantified uncertainty would require an approximation of the conditional variance.
Because in that sense, can you sort of might say that the sort of problems of computability are sort of the same, and on the right-hand side, you want to know that error all the way along, but you've only got the function evaluated at a finite number of points. And on the left-hand side, if you are caring about the distribution, you've only got a finite sample from it. So you don't know what that real distribution should
So
be.
if I were only going after the distribution, then I would have to go from the data to a density to a conditional moment that I can then evaluate, because I do want to do prediction, right? Given a new x, I want to get y. So if I only have that density, then I also have to be able to have a way to get to the conditional moments of that density. And so, I mean, I think of regression as sort of a shortcut to get to the conditional moments of that density without having to estimate the density.
You're making some
correctly.
assumption about the smoothness of the expectation.
Yes, there's also that. Yeah. Yeah, there was another thing that you said that I don't remember that I want to say. Yeah. So again, the error analysis here in the mathematical approximation theory will be asymptotic. So it's not just a given set of points, but what happens when those points go to infinity. And it's not even just the points. The points are part of a constructive procedure to estimate this thing. And then the error analysis depends on the norm of the difference, which may or may not be related to the number of points that you've taken. Yeah, thanks.
In the left-hand side, you said the standard error was estimated. So it's
Yes.
intractable as the right-hand side.
The standard error is estimated, but you have a central limit theorem.
It's also asymptotic.
That's your asymptotic.
It's also asymptotic, yes.
So it's,
So there's hurdles all the way down.
I'm not sure the left-hand side is necessarily easier to characterize.
So I think it is if you restrict your class of models for the conditional mean. So if you're always going for example, a linear mean.
But you can do the same with the right-hand side. If you restrict yourself to certain types of functions, you can actually compute these worst-case errors.
Yes, but then I lose the asymptotic properties of my error analysis as, for example, the polynomial degree goes to infinity. The asymptotics of the polynomial degree. So it's asymptotics of data versus asymptotics of the model. That's one way to think about it. But there are differences. I mean, no one would ever do polynomials of degree 8 billion in the regression case. You call it overfitting, right? But in you know, the Cheb Fund software goes up to polynomials of degree 65,000 until they get to happiness.
There is a nuance, I suppose, on the regression side. So whether it's estimating a density that's real, which would be the frequentist version,
Okay.
or whether it's just saying it's probably the case of the right-hand side, but I'm going to do some sort of Bayesian approach to trying to fit that kind of distribution.
For the sake of time, I'm going to punt on that question for now, because I recognize, one, that we have Bayesians here, and two, that the Bayesian interpretation of this probability is not quite the same. That it's more a model for uncertainty, and that uses probability. That's not quite the same as the frequentist interpretation. But for me, for right now, I'm going to punt on that. Just to give you an anecdote, when I interviewed at Mines in the Applied Math Statistics department, I was interviewing with the most senior statistician, and I said, so, you know, Bayesian versus frequentist, like, really, what's the big deal? Yeah, he didn't want me to get the job. Okay, but I do want to keep going because I want to talk about noise, about which one of these is actually a computer simulation. Which one is a better model for a computer simulation? And I think most people are familiar with these papers. So within the computer experiments world, you know, Sachs's paper from 1989, design and analysis of computer experiments, was I think one of the first. Kennedy O'Higgins model paper on Bayesian calibration computer models. I will tell you my bias and my opinion. My bias and my opinion is that I'm not persuaded that my deterministic function is a realization of a Gaussian process. It is my bias and my opinion. I think it's something that is absolutely open to discussion. However, I recognize how useful these tools have been in practice, and I am a pragmatist. So, you know, I've talked with Art Owen about this a lot, and when I say things like, yeah, you know, I just don't know, it's not, I have one function, it's not a realization of a Gaussian process. He'll say, yeah, but it works. I'm like, well, okay. Okay, you breathed in like, oh, I gotta say something.
Well, it's the question you punted on. I mean, if you really do read the second paper there, they're quite clear that it's not that the deterministic function is a realization of the Gaussian process.
Yeah.
It's the GP is their way of expressing uncertainty about that fixed and deterministic function. It's an approximation. Yeah, quite.
Well, but it's an approximation that can't be verified by experiment, and this is the issue that I have that came up at working at Sandia Labs, where there are physicists who always, if you're going to make a claim with your mathematics, you better have a physical experiment to validate it. And as far as I can tell, there's not a physical experiment. There's no truth in Bayesianism because it depends on your prior. And so, I mean, I've seen so many engineering papers where they're using Bayesian methods, and they'll pick a parameter, generate data, perturb it by noise, do a Bayesian inverse problem, and show, oh, the parameter I started with is within the support of my posterior. And I'm like, I'm just going to take my prior and move it so that my true parameter is here. And there's nothing wrong with that from a Bayesian point of view. Now, I understand it's not practical. I understand it's not practical and pragmatic.
In that sense, you can say that none of statistics is true, because you always assume a likelihood, and you could always change your likelihood to make it work, right?
Yes. That's why I personally think that computer simulations are better modeled by. I'd rather do asymptotic analysis than analysis that I can't verify with experiment. Because at least if I have an infinite computer, I can do the asymptotic analysis. Sorry,
This
sorry.
side of the room agrees.
Go ahead.
And then you
Yes.
the prior selection issue is an assumption that we make.
Uh-huh.
It's the same as the assumption of which function space you want to restrict your solution to. I think that's kind of summarizing what we were just this side of the room.
Perfect. I'm looking forward to continuing that conversation. Okay. I do want to point out that there are other perspectives on error in computer simulation than those that come out of the computer experiments literature. For example, this is a paper from the group at Sandia, Error, Uncertainty in Modeling and Simulation. If you've been in UQ a while, you've probably heard of this distinction between aleatory and epistemic uncertainty. I have never found use for that distinction of the uncertainties, but certainly people within engineering think that distinction can be very important in their modeling. I know mathematically, often aleatory uncertain variables are treated as random variables, and epistemic are treated as intervals, but it's not a world that I really live in. Here is one that I really like. So let me give you my bias. My bias comes from John von Neumann's paper in 1947 that Joe Gersher, who was a lab employee, pointed me to, called Numerical Inverting of Matrices of High Order. High order in this case is not tensors. High order means the dimension of the matrix, and high to them meant like 30 or 40 back in 1947. You can see here that the first chapter is the sources of error in a computation, and I just want to summarize what he goes through here for these sources of error in a computation. Again, when computers are first starting to come out and people are doing computations. So I've started calling this the von Neumann and Goldstein catechism, because I think that sounds cool, and maybe it'll catch on. But here's a quote from this paper. The analysis of these sources of errors should be objective and strict inasmuch as completeness is concerned. But when it comes to the defining, classifying, and separating of the sources, a certain subjectiveness, hey Bayesians, and arbitrariness is unavoidable. With these reservations, the following enumeration and classification of sources of errors seems to be adequate and reasonable. So this is a big old caveat, right? This is him saying, here's what I think about it. But with that said, I find it particularly compelling. So he goes through the following 4 sources of error in a computation. The first is the mathematical model, and this is essentially how well the math model approximates reality. Do PDEs really model fluid flow, for example? And we might call this model, well, within the context of physical modeling, we call this model form error, not in the context of model selection. Observations and parameters. So this is the bulk of the work in the UQ methods literature. This is basically forward and inverse UQ. That if I have some model that takes input parameters, but I have to set the value of those parameters from measurements, I have to try to include the uncertainty from those measurements into that specification of the parameter and propagate it forward to the model predictions. That's the gist of it. The other 2 sources of error that he talks about are what he calls finitistic, which I don't think is a word, approximations, and round-off error. Finitistic approximations means that if you really evaluate, you can never really evaluate sine, because sine is an infinite series, and so you evaluate some approximation of it. Things that are infinite series, and then round-off is numerical error and sort of the basic arithmetic computations. Now, the asymptotics for the finitistic approximation comes from classical numerical analysis. And I would call this deterministic numerical noise. Because if you repeat it over and over again, you'll get the same answers, right? As long as you don't change your compiler flags or something. But if you keep all the same compiler flags, you're going to get the same errors in here. Round-off error is also studied very heavily in classical numerical analysis. Here is my favorite quote from Jorge Moret and Stefan Wild in the paper that they wrote in 2011 for estimating computational noise. This is the first sentence of their abstract. Computational noise in deterministic simulations is as ill-defined a concept as can be found in scientific computing. Okay? So I think probabilistic numeric guys should find this paper and be aware of it. that this is, and they have a couple papers where they're trying to estimate computational noise. But I love this quote because and this is 2011, back from von Neumann's 47 paper, like we still are thinking about how do we model noise in a computer simulation, in computer computations. Okay, some summary thoughts on this, and then I'll talk a little bit about active subspaces in the last few minutes. I think UQ is more approximation.
2 hours, so don't feel pressure.
Okay. I think UQ is more approximation than regression because computer models are deterministic. Again, and I say this again, I think. This is my opinion, and I'm really excited that we can open a conversation for this. Yeah.
Yes, but if you go back to say Gaussian process regression,
Uh-huh.
and if you enforce the fact that your estimation of the mean, let's say, goes through those points, then you somehow enforce this point.
Yes.
Your regression was very loose.
My regression again, to stay concrete and simple for this talk, I stuck to polynomial regression, yes, and not Gaussian process regression, because I think that there's more to talk about there that's more complex than what I've had time to present here, including all the kernels, including choosing all the function spaces, including RKHS, including how you assess uncertainty, including are there error bounds for supernorm errors of the function approximation in terms of the posterior variance. All of those things are complicated, right? Yeah.
But if you regard uncertainty as just lack of knowledge,
Okay.
then it doesn't matter that it's deterministic if I don't know what it is. I can have uncertainty about it, which
Naturally.
I can model with probability.
I'm so comfortable having that conversation with beer. Because
But there's things you can lack knowledge about and you really cannot get more information about them. And
No,
there
I
are
can
things
get-
that you currently lack knowledge about, but you could get more information about.
It doesn't
That's
matter.
basic.
That's allowed to get more
I
information.
know,
I know how to
I think
meld that.
I'm not just saying, right,
Yeah.
down my throat, I'm just saying, in different communities, that there's kind of a sort of, there's a limit where you decide, okay, in terms of what I'm gonna do, I'm gonna use this amount of information I currently have available, I'm gonna work with this. This is where the limit of my current knowledge is, and everything else I lack knowledge about, I'm gonna model in a probabilistic way.
Mhm.
And then there are other communities who go, okay, I'm here, there's something I'm uncertain about, but I'm gonna go and find out more information about it. I'm not gonna be Bayesian yet.
Mhm.
And I'm gonna use different tools. I mean, for me, something I keep coming back to, the things I physically can't measure everywhere, right? And therefore I have to use probabilistic tools. And I use my classical numerical method to solve my linear systems of equations, right? I don't know what the exact error is, but I am not going to go down the Bayesian route and probabilistic route, because although I lack knowledge about what the error is exactly, doesn't mean I can't find out more information about it and use it in the way I approximate it.
Yeah.
So I'm not trying to present this as a war or it's one camp versus the other. I get it, and for me that's kind of the way I describe it to myself now. Kind of, it's important, you know, in terms of discussion about lacking knowledge. In the numerical analysis community, we do lack knowledge, but we don't go down the same route.
No,
Right.
there are lots of ways to solve the same problem, but to say it's.
But if they're
it's
different
not
problems,
regression
then don't
because
use the
it's-
same way.
Because it's deterministic, it doesn't mean we can't use probability-based methods on deterministic problems because they're problems of lack of knowledge. And the fact
Right.
the underlying thing is
So-
deterministic but unknown
So I think
means
words,
I can use those methods.
I think words like knowledge and information have to be precisely defined.
I think that
they-
nobody's saying that
but
approximation
in-
doesn't have its place and regression has its place. And we're not trying to say regression is better than anything. I think it's just the
Sure.
straw man of regression as a sort of modelling things with random processes in a sort of frequentist sense. That's all we're objecting to. We're not saying, aha, we're better than approximation
Yeah,
theory
sure.
at all. We're just trying to give a slightly more nuanced flavour of the other side of that.
And-
That's all.
And I appreciate that. Again, I wanted this to start the discussion.
Yes. Yeah. So, you see, I would take your first thing and I would say UNQ is both regression and deterministic and approximation depending on the context.
Yes, but my but here for my second statement was, although that I think that the computer models are deterministic, computational noise is really annoying if you take it seriously. Because even if you take it seriously, then you have to add a nugget to your kernel. What's that? Because why you don't want to go? Why do you want to pass through your data exactly?
Well, but adding a nugget to your kernel is assuming that your computational noise is Gaussian, right? Which we know computational error is not
Right.
like Gaussian.
Well,
distribution.
I was thinking of it more as a term for regularization so that I did not have to interpolate my data, which is the effect of, I mean, I think that I can add a kernel and say that it is a way to regularize my model without assuming Gaussian noise.
But then you're not you're not modeling computational noise anymore.
I don't know, am I?
Well, so adding a nugget to your kernel is the same as saying that the observations that you've obtained are Gaussian distributed, have a Gaussian error.
I think assuming the errors are Gaussian leads to a nugget in the kernel, but I don't think it's the other way. I think that that's like saying I'm going to use least squares. Least squares doesn't imply that I have Gaussian noise on my model.
The functional form of the estimate in each case is the same, whether you assume Gaussian noise on the observations you've obtained or whether you add a nugget to your kernel. So I think that implicitly when you add a nugget to your kernel, you're assuming that the information that you've obtained is Gaussian, is drawn from a Gaussian distribution.
No, you could just take a T nugget. I mean, you don't have, no one's forcing you to use a Gaussian nugget.
What, like adding to the covariance matrix an identity?
I think of that
If
as
you're doing
One
Gaussian
could.
process regression.
as a regularization.
One could do T process regression and add T noise if you really wanted to. It doesn't, yes, you're probably making some assumption about that distribution.
Yeah.
But I don't think it has to be Gaussian.
Yeah, okay.
And generally
But
it is.
my wider point is that you're making that I think the two are the same. Whatever nugget you add, you're assuming adding a nugget is the same as assuming some distribution on the observations that you've obtained. And if that doesn't respect the computational noise, which
But I think noise leads to regularization, but regularization does not imply noise. I think it's a one-way implication. But
But I must say that in my experience, maybe the others can comment, but the computational noise is often minuscule compared to the, I mean, in my experience, okay?
yeah,
In the types of models I've been looking at, but, and therefore, this is not the main issue. I mean, sure, sometimes it's important, but
I will tell you that in the models that I look at that are complex multi-physics that include fluid flow, that if you perturb geometry parameters, you get a crazy jump in things.
so maybe we're not talking about the same computational noise.
Right. I'm talking about a whole range of computational noise that leads to your functions not being smooth.
So what is computational noise? Is when you vary some parameters, or is it when you redo when you run again the computational experiment, you get different answers? What's
No,
it?
you don't get different answers. You always get the same answer.
So that's what, yeah. Okay. So first we're not clear on this, and then so it's what is it, computational noise? Even though we struggle with it.
I like these four things. I like this classification of them.
Yeah, approximations, but that's typically.
So I agree with you that these are typically small.
Yeah.
But back, and actually no, it's convergence in this thing. It's a fixed point method to solve for your fluid flow. That's not converging because your fluid flow has sharp fronts in it or something.
Yeah, you're far away from the. But then.
No, it's just the matter of the physics. That's
Yeah,
just
you don't respect
approximating
the
the
physics.
Yeah.
That's true, but that's not taken care of by the. I mean, I don't feel that it's taken care of by the approximation of the regression. That ought to be taken care of.
If there are errors here because you have a fixed point method for solving for your fluid flow or the solution of your PDE,
Sure.
and then your F, that is your output, is some quantity of interest from your PDE, then the error will potentially, not always, potentially propagate to the output of that PDE.
So that's getting to the epistemic discussion, epistemic uncertainty discussion. So the model that you're running is not respecting well the physics, and therefore your approximation of that.
Yes, the engineer would say the model hadn't converged.
Yeah, but we still use it also. But how do we blame either the regression or the approximation for not taking care of something that nobody has taken care of in running the computer model? It's very difficult.
I'm not blaming it.
Yeah.
In fact, I'm saying that it's really annoying if you take it seriously, but I think most of us don't take it
Yeah,
seriously.
exactly.
That's my point. And I think for the real computational scientists that I see running really big problems,
Yeah.
they look at UQ and they're like, you guys assume way too much in your methods. That's been my experience talking to a lot of the computational scientists.
Yes, no, I would agree with that. Yes,
Practical suggestions. We did this one. Civilized conversation. I think we're doing good. Yeah. Nobody's mad at anybody else, right? Good. No beefs. Statisticians. I would encourage you to include numerical experiments that demonstrate asymptotic convergence of testing error. And when I say asymptotic, I don't mean I did 100 runs and then I did 200 runs and then I did 400 runs. I mean do 10, 100, 1,000, 10,000, 100,000, and a million. Well, but in most of the computer experiments papers that I've seen, they are using functions, at least the first function, they very often can't afford to. And so I think you should include a function where you can study the asymptotic convergence of testing error on some particular function.
Sorry, what do you mean by
testing error?
Yeah.
Out of sample testing error. So you have a training set and a testing set.
Mm,
So you mean model
So
validation?
increase
What I would call
increase
model
training
validation.
data. Say it again.
I mean, what I would call model validation.
Okay, so model validation means something different in
Okay.
physics.
Yeah, I said what I call model validation.
But yeah, sure. So you fix some number of testing points, you take your training data to infinity, and you check that the asymptotics of that. Now, again, the computer experiments papers that I have seen, you know, they're like, well, we use 1,000, and then here are all of our experiments. And I was like, I really want to see, if you're going to use a function that you can evaluate 1 million times, I want to see asymptotic convergence. Numerical analysts. Convergence analysis of statistical standard error and bootstrap standard error in the context of constructive approximation. Yeah, I think this sounds really interesting, and I don't know how to do it. But I think that these are practical and computable in ways that a lot of the numerical analysis kind of a priori estimates are not computable, or even many of the a posteriori estimates. But I don't know how to do convergence analysis of them for the constructive approximation error, if it's possible. And then write 3 papers. We should write regression for the numerical analyst, approximation for the statisticians, and some reconciling perspective with authors from both communities. So whoever it comes.
So do people use the bootstrap in that context?
I do, but it doesn't seem like it's very common.
I tend to do that too, but I'm not.
But it's not very well justified. It's very ad hoc.
Yes.
Okay, who wants me to do this? Because you've already been sitting here for 55 minutes.
Can I just go back to your...
Oh, yeah.
I'd just like to comment or talk a little bit about the statistician's
Yeah.
point there. So often what seems to happen is you devise a method and you show it works on your pet example, but the real question is it going to work on a different example? So I'm not sure how.
No, my question is that on your pet example, assuming that you have some pet example that you can run 1 million times,
Yeah.
I want to see asymptotic convergence. Like so in numerical analysis, if we are studying the numerical approximation of a differential equation, ODE or PDE, we will get the grid size, we will do a range of grid sizes that become fine enough until we can verify the asymptotic analysis of the convergence rate. And we can see it. We can see it on a plot. And there's usually a region before it kicks in, and then a region where it looks good, and then a region where round off kicks in and we don't see it anymore. And so, but this type of plot, the slope of this line is related to our asymptotic analysis, our a priori analysis of the numerical method. And we do it on the heat equation or whatever, something simple where we can really like drive that error down as much as we want. And now you might say, we proved root and consistency.
So one of my favorite quotes was, "Asymptotically, we're all dead." And if someone gives me 100 runs, a budget for 100 runs, I get to choose where they are and stuff, and it's going to be on a supercomputer. And I first come up with a method for trying to do this stuff. Do I care about asymptotic convergence of that error?
No.
Given that I'll only have 100 runs.
But that's not a study in the methods. What I'm talking about here is that if you're going to publish a paper that is proposing a new method, then I want to see a numerical experiment.
I would absolutely try and publish whatever I came up with as a new method, but it would be a method for, say, data of about 100 or 200. It's something practical, like the asymptotics are. I know it's
again,
worthy of study in some areas, but for many of us, it's kind of like, well, I'm never going to have 1 million runs, so.
But it's still a property, I would argue that it's still a property of the method that's worth exploring.
Well, okay, part 2 of that question.
Because part of Catherine's point about solving a linear system, I don't necessarily know what the error is, but if I did a little bit more work, then I could get a smaller error. If I know I go from single to double to quad precision in solving my linear system, I believe that my error is going to get smaller, even if I'm using a LU factorization and getting it to numerical precision.
Is the best method for 100 runs the same as the best method for 1,000,000 runs?
I have no idea, and I think it's highly problem dependent.
But if you look at, I mean,
Also, yeah.
a very different problem, but it's the same idea. If I can only ever collect 5 numbers
Mhm.
from some constraint, there's little point in doing analysis that there's 1,000,000 numbers and the central limit theorem kicks in and everything's nice and normal. When my 5 numbers, I know it's nowhere near going to be normal, and I need methods that are not asymptotic. I need small sample methods, and a lot of the times we're working in small sample area.
So if you publish a paper for small sample methods, that's fine. But if you publish a paper that's based on radial basis function approximation, Gaussian process emulation, then I want to see this asymptotic convergence rate.
I mean,
Sorry.
so when we have an undergraduate student, right, and they're learning some numerical analysis for the first time, maybe some finite difference methods or something, and they're using, they've got a computer program, and they're showing me some results. Here's my code, it works. And I say, how do you know it works? It didn't break, right? Usually that's the first thing. And I go, okay, you know, what can you do to check that somehow this method is doing the right thing? What does doing the right thing really mean? Okay, well, the method has associated with it some parameters. It might be a time step, it might be a tolerance, it might be a mesh size, something. And there's some theory out there that tells me, I don't know what the true error is, but if I change this parameter, my approximation should be more accurate.
Yeah. Within the asymptotic regime.
And I said, what could you do to somehow check your code? Well, I could go away and I could run it with a smaller time step, or I could make the tolerance smaller. Okay. And if by doing that, the solution goes bananas, then you know there's something wrong with your method.
Yeah.
Because the theory tells you what ought to happen. So it's not that I'm going to make them run their code until they've exhausted all the memory in the universe to track that it really is. But you need that assurance of consistency and that something is getting better as you refine, enrich your approximation, or enrich some, or refine in some sense. Because if I don't have that assurance with my method, what's it good for?
Well, we tend to check by either holding data back and predicting the data we've held back, or leave one out.
Yeah, but I'm asking you to do that and then increase the training data, which Catherine very nicely called enriching the approximation.
Well, it's slightly, I mean, we do sometimes have slightly different objectives here. So take Danny's problem of 100 points. So the output of that, of your analysis based on those 100 points might be a distribution for some fixed quantity. It's a bit like when you use a Gaussian process in your sort of approximation setting. So the functions are drawn from the function isn't a draw from a Gaussian process, but you think a Gaussian process is a reasonable way to represent your uncertainty about a fixed function. And so when we're thinking about validating, kind of what we want to, well, what some of us care about is that distribution that we are, does using this method produce generally well-calibrated distributions? And claim to be 95% certain, are you right 95% of the time? And it's that sort of validation I think we care about, as opposed to would it work? You know, would you converge to the right answer? If you were to,
which is more closely related to, say, a simulation for coverage.
Yes.
Yeah. I mean, and that's the standard simulation if you were judging methods and testing asymptotics and statistics. What I'm communicating to you is that in the context of approximation, we have a different way of testing methods and judging their approximation. It's based on verifying the a priori asymptotic analysis, just like what Catherine just said. And so if we want these, at least you need to know that that's how we judge methods. And so when I read papers from computer experiments and they say, we did it with 200 and we did it with 400, I'm like, you're not telling me that that it's working in the sense that I understand how to test that something is working. But yes.
Yeah, I think we should follow these points. So indeed, having a nice asymptotic result about the convergence of or technique, whatever, may convince you, but in practice, it might be going the wrong route, I shouldn't say those words long, but indeed, in computer experiments, we definitely are in a situation where we cannot have many runs. We're struggling with that, and therefore we have to come up with methods that target that specific regime of operation. So we may end up in a situation where we, for a mathematical comfort, we would prove results or show asymptotic numerics that demonstrate that our methods are fantastic, and we can tick those boxes, but in practice they may not work for the problems of interest
Yeah.
that we want to target. So there's a tension here.
I don't think it's
convincing-
tension. I think it's I think they're independent axes.
I see.
I think that you ought to do both. I think that if you're going to show me how your method works on some problem where you can run a million, which I've seen in every computer experiments paper, they pick some function of a few variables, or they pick some simple ODE, and then they demonstrate what happens. But if you can run
It's
that
not
thing
the
million
point.
times,
If in a for classical statisticians or frequentists, sure. So the idea is there's a true distribution, and most papers in statistics are probably asymptotic theory papers showing that some estimator is
It's
getting
root and
the
consistent.
true value of those parameters in some sense. But in UQ you won't find many of those statisticians because of the deterministic problem. Instead you'll find Bayesians who aren't interested in that at all. They're expressing their own uncertainty about something, and so they're calibrated in the sense that Jeremy said, you know, if I say it's true 95% of the time, then that turns out to be the case when I run it. If I have 1,000,000 points, I do something different to if I'm going to have 100 points. I don't set up methods for 1,000,000 points, and that's partly because I don't think there is a true setting of the parameters of the Gaussian process that's going to mimic the function. I don't think that. But I think that on the order of 100 runs, it's a really good way of expressing my uncertainty about what's going on in the middle.
So I'll tell you my concern with that perspective from the physical modeling point of view is that a physicist and an engineer believes that there is a true value of the parameter. A physicist and an engineer believes that if I could do the perfect experiment, if I could do the most expensive, if I had infinite computing power, if I had infinite money to build the biggest machine, I could get as close as I wanted to, which is an asymptotic statement. I get as close as I wanted to this true number, and I'm representing for you the physical model, the physicist's perspective, and so I can tell you that Tim Tricano was a senior scientist at Sandia when I was there. I think, and he's still there. But we were sitting around talking about things like this one time, and he said, if you and you know, at the national labs, there is a group of physicists behind a wall that nobody ever talks to because they're modeling nuclear weapons. If you walked in there and you said, I'm going to replace your physics with some kind of probabilistic model based on Gaussian processes, they would just kick you out of the room. Because they don't see the world that way. And I respect that as their culture. And so when I think about the applied mathematics behind approximation theory, I think of it as being closer to their culture in the sense of I can refine my approximation, enrich my approximation space, and get closer to some true value that's actually there.
But when it's stressful, when we are actually solving complex problems,
Yeah.
we don't all only solve the elliptic field all the time. The elliptic field is our test problem.
Right, absolutely, yeah.
We know that we have finite resources as well,
Right.
so we don't
Yes.
keep doing experiments until we necessarily, often we have to apply the method and we get one shot at it. But by doing these convergence studies, these asymptotic studies on test problems, what it allows us to do is to understand the properties of the methods. We know what the error depends on and how.
Right.
In the classes of problems. That doesn't mean that we might then have to go and use it in a context where we don't know precisely what the error is.
Right.
But it's kind of the way that we validate our methods.
Yeah.
There's also the kind of tests we do. We'd really like, and again, it comes back to the difference between uncertainty bounds and error bounds. We'd like to understand what the errors are, what things that are under my control that they depend on.
So
So if somebody else were to take this method and go away and use it in a slightly different way, where something was slightly different about their problem, they had slightly different mesh, they had different kind of source term in their problem or whatever, they could take that method and they could understand how it would behave on their problem, which has features which are slightly different.
So do you have the same, do you run into the same situation that Danny described, where if you had many points, many runs or whatever, you would actually use a different method than for a case where you have a few points?
Actually, what I would do is I would use it to check the accuracy of the method, because getting an answer takes one cost, and checking that it's a good answer takes more cost. And so I would use that as a big testing set, and I would say now, oh look, I did it with my 100 runs, but I've got a billion, so I'm now going to check it on 990.
And what if the method that's asymptotically valid is not very efficient for a small number of points? What if it is the case? And it's probably the case.
I think it's often the case. But here's the other thing that I would say within this room, I would rather us make the comparisons at the level of the theory first, and then discuss the practicalities, because I think once we get into that soup, it's there's all kinds of dirt in there, and all of us sweep stuff under the rugs, right?
But the assumption in approximation theory, if I understand it rightly, is that there is a function from some function space with defined properties. That's assumption number one.
Okay.
And then you have
Finite
you're doing
variance.
the best approximation from some class.
Okay.
Therefore exists, and in principle you
Sometimes
can find
it exists.
Well, I mean, okay, but you can prove when it exists, but you set the problem up in a way that you're looking for a truth. And no doubt that many statisticians do that with data analysis in the way that I described, but you won't find them in computer experiments. It is a different philosophy. We don't have that assuming that we're looking for a truth. We're trying to express the fact that we don't know what's going on.
But the weird thing about that is, like in computer experiments, maybe more than anywhere else, there is a truth. That if I had the biggest computer, I could evaluate my model at every floating point value in the space.
Sure, but the truth, unfortunately, doesn't lie within your function space most of the time.
Right, so then there's this, it's this problem of how do I know how to enrich my approximation if I don't have asymptotic approximation to the truth?
Well, you have asymptotic approximation to a truth if it was in that function space.
Right, but you just said it's not in that function space.
Probably not, because the physicists are probably wrong. The physics is probably not right. There probably isn't a true value of the parameters.
But then it makes a difference which of those errors you're talking about.
Sure.
And I'm not talking about that model form error. I'm talking about the computational model's approximation of the mathematical model's solution. And that mathematical model's solution, we have proven that it exists in many cases for PDEs or for whatever. Right? I agree with that. I mean, that does math represent the reality is another bigger conversation.
It's not to knock down either side, but I actually think we're making some progress on a sort of difference between the perspectives of the community. I find it really interesting.
So who wants to hear about active subspaces? We're almost there, and then Jeremy was like, wait a minute. 15 minutes later.
If you go back another 5 slides, no.
A little bit? Okay. How about this? Stop me if you've heard this one. That's how we do jokes. Okay. The main idea of important subspaces. Right? So I have my function of many variables. Many of them meet M for many. And think of off-axis screening or global sensitivity analysis. And that's the gist of the idea behind important directions, or the span of some set of important directions, which would be an important subspace. Active subspaces is one way to try to do it. How many of you have already seen this movie? Because I show it a lot. Yes? If everybody's seen the movie already, Jeremy, I don't think you've seen it. No.
Was it your workshop talk?
Yes.
I wouldn't mind seeing it again.
Okay.
So good.
It's a minute and a half. So you have your function of two variables, where two is many. You take a top-down view of this function. You imagine sampling independently and randomly according to the input space, and at each of those points evaluating the gradient of that function. You take this collection of gradients and identify a relatively important direction that's off-axis and an orthogonal direction that's relatively unimportant. You imagine rotating your perspective of this function so you see that variation along the important off-axis direction. You choose points in this sort of domain in the range of this important direction, And now you actually want to estimate conditional averages. For each of these points here, you want to sample your function a few times along the less important direction, which also gives you a chance to validate that you found the less important direction. You collect all these pairs of input and set of outputs from which you compute conditional averages, the blue dots, and now you can fit a curve, and your one-dimensional approximation derived from data that came from a two-dimensional function. You extend this into and out of the screen, and now you have your two-dimensional approximation for your two-dimensional surface, which is intrinsically one-dimensional by construction. Okay? So that's the big idea behind active subspaces, is finding these relatively important directions that are not necessarily coordinate aligned. All right, I didn't have time to go through and make these all sort of appear one at a time, so please don't skip ahead, just follow with me. So given some deterministic function and given some density rho, the active subspaces are just eigenspaces, and they're eigenspaces of this particular matrix, which since we have the density, can be written as this integral of the outer product of the gradient with itself. The integrand here is a rank 1 matrix, but it depends on x. When I average or take the expectation with respect to this density, I get a symmetric positive semi-definite matrix. This is a comparison with PCA. PCA, uncentered, is derived from the eigenspaces of this matrix, expectation of XX transpose, which has integrals, assuming we have this density, can be written like this. Now, note, both of these are based on eigenspaces. Both of them require some decision for the reduced dimension. However, there's no function in PCA. Right? Notice there's no f in here, and the reduction is independent of any given function. So if you have some function of if you have two different functions of x's, then this matrix will be the same because it doesn't depend on f, but this matrix will be different for each of those two different f's. The active subspace reduction is entirely dependent on the function. There's no centering in active subspaces, and that's really important because typically the average gradient turns out to be a very, very important direction. If you consider the function f of x that's just 1/2 2 norm of x squared, then you get that the gradient of that function is just x, and then these two matrices are the same. That, as far as I can tell, is the only case where these two subspaces are the same. So, isn't this just PCA of the gradient? No, because I don't want to reduce the dimension of the gradient. I have no interest in reducing the dimension of the gradient. What I care about is the relationship between the dimensionality or the rank in some sense, or the decay of the eigenvalues of this matrix, and the relationship between x and f. And that comes through you can write the eigenvalue as a Rayleigh quotient, and get that the ith eigenvalue is the average squared directional derivative along the corresponding eigenvector. Which means that if this matrix has a null space, you can think of as a zero eigenvalue, then you have a direction along which that function is flat. Okay? So far so good.
And this works for any row at all. There's no assumption on the distribution of the inputs.
I can't think of any. I mean, there's probably some kind of continuity with respect. No, I can't think of anything. Anything, and it's really anything you can compute an expectation as, which means this doesn't have to be a density. You know, this could be supported over some strange set, and this could just be an expectation of those gradients. Okay, now when it comes to computation, meaning estimating this thing here, the active subspaces can be estimated with the SVD of this matrix, where now each of these x's and these weights come from a quadrature rule. Why is it a quadrature rule? Because I'm estimating integrals. PCA uncentered, again, is computed from the SVD of this data set for data that's drawn from some distribution. In most data applications, this distribution is not known. You're given data, you assume that it comes from some distribution, and you estimate this covariance matrix. But again, I'm just pointing out the difference here, that in this case, the reason that I have some matrix form of this is that it's related to estimating an integral. So it comes from this numerical quadrature rule. Comparison with PCA. Comparison with manifolds. Given a deterministic function f of x and a density, we started there before, versus given a data set where the data set is drawn independently from some potentially unknown density. The problems are just different. As far as I can tell, the problems really are different. If this x, let's say it contains pairs of inputs and outputs all stacked up into the same vector, you certainly could apply manifold learning to it, but I don't know what you would get. And I don't think it's a good idea because you are ignoring the independent-dependent variable structure of the problem if you do that. You're just saying it's from some joint distribution. However, if this function is really deterministic, then that joint distribution does not have a density. And if that joint distribution does not have a density, then a lot of the analysis or the errors of the manifold learning doesn't apply. Moreover, the manifold doesn't provide a surrogate for the input-output map, which is often what we want in practice. We are working right now on extending the idea to f of x where the inputs do come from some kind of manifold, specifically in shape optimization, where the input might be the shape in some kind of a domain of a PDE. Fisher information matrix. So given a deterministic function f and density rho, active subspaces are eigenspaces of this matrix. The Fisher information matrix is written like this. So the conditional expectation given parameters theta of the gradient with respect to the parameters of the log of some density, which can be written like this if you have that conditional density. Now, note, this thing is a conditional density, and the derivative is with respect to theta, but the integration is with respect to the data. So if you take this matrix and then average with respect to theta, then you get something that looks closer to this, where now you have to interpret this f as the log of a probability density function. Let's see. So if you take expectation of Fisher information with respect to theta, Mark called this Bayesian Fisher information matrix and cited someone named Van Trees from signal processing. And in that case, you are interpreting rho as the prior on the parameters. When I said Bayesian Fisher information matrix to Art Owen, he said, whoa, that's like clash of worlds in statistics, which I think is pretty funny. But a lot of people look at this and they're like, oh, this is just the Fisher information matrix. And I go back to that, like, don't be so reductionist. You have to be really careful about what Fisher information matrix is, what are its components, and how you want to interpret this potentially, and in which cases you can interpret it validly as Fisher information matrix. Optimization. So these two lines are the same. If you have a gradient descent method for optimization, for an optimization problem, it looks something like this. So given the step that you're currently at, the next step is you just subtract some multiple of the gradient, where that alpha is a step size. For a Newton step, you multiply that thing by the inverse of the Hessian matrix. Really simple comparison. Optimization methods are local. They're occurring at one point in that parameter space, whereas active subspaces are global in the sense that they're averaged over the entire parameter space. Now, you can start to play games with rho here. So if rho is a delta function at one particular point, then you'll get back the outer product of the gradient at one particular point. How might you exploit the active subspace to accelerate optimization? Well, if this matrix is truly rank deficient, meaning you really have a null space, then you wouldn't ever want to move in those directions in your gradient-based methods. So I can imagine this as a pre-processing step to see if there is actually a null space to then reduce the size of your gradient-based optimization methods. However, I don't think no one would say like, yeah, but you're going to reduce it some number of dimensions. Like I could have done that. This is not something that scales very. The scaling is not very difficult with dimensions. This thing, these steps. Certainly with this one, which is why everybody uses it for training neural nets. Inverse regression and sufficient dimension reduction. These two lines are the same, again, for active subspaces. Again, let's remember the regression problem setup. I'm given pairs, predictors, and responses from some unknown joint density, and regression seeks to characterize the conditional random variable of response given predictors. Sufficient dimension reduction is a dimension reduction on the predictor space for the regression problem. Seeks a tall matrix A such that the response is independent of the predictors given this particular compressed version of the predictors. This took me a long time to unpack. So if you don't get this, I'm more than happy to go through this sort of on the board. Inverse regression seeks to characterize the predictors given the response. So if you think about a two-dimensional predictor space and some one-dimensional response, you can imagine slicing through the response and considering all of the predictors that map to that response. Sliced inverse regression uses eigenspaces of the conditional moments of the inverse regression to try to look for this matrix A. Sliced average variance estimation uses the conditional second moments of this inverse regression to try to find A. Now, what does this have to do with computer experiments? So a function is called a ridge function, means that f of x can be written as some other function of a few linear combinations of the x's. So let's say that A is a tall matrix, and let's say that it has full column rank. For active subspaces, if the function is a ridge function, then that matrix is rank n, and also if the matrix is rank n, then the function is a ridge function as long as it's continuously differentiable. That's the necessary assumption to go from this way to that way. For the inverse regression and the sliced average variance estimation, in the population case, I haven't done any sample kinds of methods yet. If your function is a ridge function, then the rank of that matrix is n, but not the other direction. There's a counterexample. Same thing with save. If your function is a ridge function, then the rank of this matrix is n, but not the other direction. The nice thing about these inverse regression methods is that they don't use gradients. So a lot of people want to use them to do dimension reduction in context of computer experiments. But you need to be really careful how you define expectations in the noiseless case. And in fact, working on this type of thing with my PhD student, Andrew Gloss, this is really where the distinctions between regression and approximations became really, really clear to me. Because understanding how to define expectations when there was no noiseless case for these weird inverse regressions, it took a lot of time to dig into that. Analyzing the analog of the sample estimates of these population matrices in the noiseless case also took some work. And what basically the gist of it is we can analyze these as some really strange integrals and then treat a Monte Carlo estimate of those integrals as sort of what would happen in SIR and SAVE. Kernels, given some function, blah, 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 same thing, active subspaces are here. For kernels, if you're given a data set and some kind of a map from Rm to Rm, the kernel matrix has elements that look like this. So some notes. The kernel matrix has dimension that depends on the data dimension, is capital N by capital N. It's how many times you sampled this thing. The matrix for active subspaces dimension that's dependent on the parameter dimension. These two are certainly not necessarily, are not necessarily the same, are typically not the same. There are kernel methods for dimension reduction in supervised learning that are related. Fukamizu and Mike Jordan have some papers on this. But essentially, the way that I would interpret them in the context of estimating this matrix is they build a radial basis function approximation to f, compute its gradient, and then average it, along with all the sort of niceties that get worked out because of kernels. This is the last one. Note that if you want to estimate this matrix, you have to estimate derivatives and integrals. So maybe, oops, this is supposed to be difference. You could do finite difference approximations derivatives. You could use some kind of surrogate or model approximations of the f of x, for example, polynomials, piecewise polynomials, local polynomials, radial basis functions, which start to look like kernel methods. There's a group of people sort of from the polynomial chaos world that want to estimate this matrix by first fitting a global polynomial to f, then estimating its derivatives, and then estimating this matrix. I think that's a little funny because fitting the polynomial is something that suffers from the curse of dimensionality, and the whole point is to try to use this to reduce the dimension. And then finally, like any integration rule that you use up here, in principle, gives rise to a different method.
Well, that if you use kind of sparse polynomial techniques, the whole point is it can be independent of the language.
But then it depends on sparsity, which you don't know.
Well, yeah, it's not going to work for all problems, but depends what f is, right?
Sure. Yeah, and yeah, in fact, what Xu Yang wants to do, or has a paper on, is using the rotation that comes out of the eigenvector matrix of this matrix and try to rotate the domain of the function to increase sparsity in a polynomial representation, specifically Hermite polynomials for Gaussian inputs because they're rotationally invariant. However, his method is not actually, he just has this like weird fixed point that, or alternating thing that goes back and forth. It's not clear at all that it's actually optimizing anything. Okay, so I took only, another 15 or 20 minutes to go through all that. But that was the most voted for question, is how do active subspaces relate to all of these other methods? And we're not done. I mean, this was just all I had time for between last night and today at 2 p.m. Yeah?
Could you go back to the slide of the functional principal components comparison, or just the principal components?
principal. Sure.
There it is.
This one? Or this one?
That one,
Yeah.
yes. Yeah, so so you mentioned that you're not trying to reduce the dimension using these guys, but it is
Not
a
of the
dimension
gradient.
reduction. Not of the gradient.
Right.
I see.
I want
Yeah,
dimension
the
reduction in
particle
the
is
x
in-
so that I can have an approximation of my function. That looks like this. Where now these linear combinations are coming from the eigenvectors of that matrix.
I see. Okay, and so, I'm sorry, I don't know the literature very well.
That's fine.
So how do these dimension reduction techniques then compare to other existing techniques? Like they're, I mean, that's kind of a really big question.
I was gonna say, what do you mean?
No, I mean, right, no, not in this sense, like whether or not they're the same or not, but I mean, like in terms of convergence, let's say, since we've been talking about.
So the only other dimension reduction techniques that I know of are coordinate based and would be based on, say, screening or something like screening. So you screen, you have 10 variables, you do some screening, you find the most important 3 or 4, and then you ignore the remaining 6 or 7. And honestly, as I read the sensitivity analysis literature, there is not enough literature on what is the effect of ignoring the unimportant variables on whatever problem it is that you want to solve. But I think about that a lot in this case.
So I wonder if this has a relationship to what we were discussing before, like you obviously are trying to reduce the number of active subspaces that you're working with. So I guess you'll be, in some sense, you want to show that obviously as you increase the number of subspaces, your approximation becomes better and better. Is that
Well, yeah. So this is if these are eigenvectors, then once you include all of your eigenvectors, then you're back to the original problem.
right?
So,
Thank you.
but it's not necessarily asymptotic because it's finite dimensional.
I see. So it's related to the problem of screening, but
Yeah.
it's done in a kind of more principled way, or I guess.
Yeah, well, it's off-axis screening. I allow a rotate. You can think of it as allowing a rotation before doing screening, or doing the rotation and the screening at the same time.
My only worry with this sort of method is that, looking at your little video,
Uh-huh.
I would have blown my computer budget before I was halfway through that video.
Yes. The analysis that I don't have in these slides is how we construct this G function, and the way that I did it before was for each of the points in the active variables, I sampled a few times in the inactive direction. So that can actually, as long as those eigenvalues of the inactive space are small enough, then what that means is my function doesn't vary much along those directions. And I want to estimate the conditional average of fixed the active variable, what's the average over the inactive variables. But if my function doesn't vary much, I don't need that many samples to estimate an average. How many samples do you need to estimate the average of a constant?
If I know it's a constant.
Yeah. If you know it's a constant, 1. But if you can estimate that variability, and in fact, the first paper that we had that came out in CISC, we used the inverse of those eigenvalues as correlation lengths for a Gaussian process, like an anisotropic Gaussian process approximation along the coordinates defined by the columns of A.
Yes, actually, I wonder if you could. I mean, I'm a fan of this method, so you know that I've used it.
Thanks, me too.
But I wonder if you, following what you just said, I wonder if you could even improve the sampling, knowing that these variables are more or less active.
Yeah. So if you can estimate this matrix, then I believe that you can take advantage of any anisotropy that you find from those eigenvalues.
Yes.
Some people have asked, how do you estimate this matrix?
Sure, but let's say.
But yeah, I mean, you could do any kind of min-max sampling based on a distance norm that looks like xi minus xj with that matrix as the norm. So, write it. So this transpose C xi minus xj. So you can, and actually you probably want to add something like a little nugget so that it's not, if it actually is rank deficient.
What is C? Yeah.
Sorry, yeah, C is the average outer product of the gradient. That this turns out to be a really good matrix for, you can think of this as like an output dependent norm for something like minimax or max-min kind of sampling. So I've done some numerical experiments with it, but there's no analysis as far as I can tell. I mean, I can say it's a good idea and I can show some numerical results, but I can't do any analysis.
Is there some sort of notion of local active subspaces?
It sort of depends on whatever you think that rho is. I mean, you can always take rho to have a relatively small support. I mean, it's sort of like our sensitivity analysis conversation we had the other day, right? That you could have a very big space that you initially do your sensitivity analysis with respect to, but then as you change the support of rho, potentially your active subspace would change dramatically.
But have you thought about like estimating them?
I haven't needed to. I typically am looking for some kind of global property of f of x, and I think of that rho as given, that God has given it to me, and it's not something that I'm going to play with.
Sure, it's interesting that if you had grad f,
Mhm.
then in some sense you're getting you almost have a sense of how the active subspaces are changing.
If
Assuming some uniform row, for example.
Sure. Then just grad f transpose. Then that's just the integrand. And the way, I mean, I wrote the SVD version of estimating that, but really it's a sample approximation looks like, well, let's say 1 over n. Let me be more general and put my integration weight here. So if I estimate this thing, where this is a quadrature rule, and grad fi is my gradient function evaluated at my quadrature node, then you can think of like each of those evaluations, I'm sampling, or some sense testing the gradient at a bunch of different points in the space, and then taking just a weighted average of them to estimate that matrix of integrals.
I'm just thinking it's a global measure for something that for lots of problems you could imagine was, there's this space over here, there's this space
Sure.
over here.
And if you average them together, then you won't, if you have a two-dimensional space, a function of two variables that varies this way in this part of the space and this way in the other part of the space, you average it together, then you just don't see any reductions.
Mm-hmm.
Yeah, I'll tell you in my experience, statisticians really upset about this thing. Really don't like that row. I'm like, it's given.
That's just fine to me.
Well, yeah, I see. Yeah, basically, it's prior. Anything else? Yes.
Am I allowed to go back to the previous discussion?
Absolutely. Turns out that's more interesting than the one you all voted for.
Just a question. So in terms of sort of demonstrating asymptotic properties, is it because you directly want to know what those asymptotic properties are, or is it also perhaps because there's something about the method as used that you don't trust and you want to see that validated via an asymptotic test?
So, in my experience, sometimes we devise methods where we don't necessarily know the asymptotics, but now I can test it numerically. Right? And if I know the asymptotics, then I'll test it numerically to verify that the code is working. But I don't know, maybe you have more to say about this.
So let's suppose, for example, just doing function approximation with a Gaussian process, and when you ask for some sort of asymptotic demonstration, is it because you want to know the asymptotics, or is it because there's something about the Gaussian process model that you don't trust?
Yes, I say that would be
One
first.
of the points.
that would be the first.
Right. And I'm trying to get
kind of validation of your numerical approach. I think numerical analysis teaches to be mistrustful of numerical methods.
Yeah.
There's numerics, and there's numerical methods that come with theory. Anyone can do numerics.
Right.
And we'd like some reassurance that when
Yes.
we use numerical methods, they are sensible in some way. And this is the way that we have devised of checking that they're sensible and valid ways to approximate. I view Tony O'Hagan, this has been recorded, but telling me I'm not allowed to use the word approximation when I say I'm going to represent a function with a Gaussian process. To me, a Gaussian process is a function. It's a class of functions. They may be random functions, but they're functions. And I would like to do something that shows me that's a sensible class of functions to use to represent the thing that I don't know.
But in a sense, we're not using it for that purpose.
Okay.
We're using it to express our uncertainty about that thing. We're not
Why
saying
do you
the
use
thing
that
draws from a
over
Gaussian
some
process.
other choice of
We could.
function?
We could choose something else if we wanted to.
But that's it. What is the
But that uncertainty is so dependent on the choices of that function space, whether it's the parameters of the kernel or your prior or both. Because your posterior variance, I can make it do whatever I want by just fussing with the kernel parameters.
It has to be a sense of, okay, I'm going to do something, but there's some, but, what am I trying to say? It has to be a way of making better what you're doing. It's that question of theoretically weak. Sometimes you just have one shot, you do one numerical experiment. But in theory, something about what we do should be able to be made more accurate or better somehow. And it's that mechanism by making the approximation better that we want to test. Be that changing number of observation points or number of runs or the mesh or whatever it is. I want some assurance that when I change one of those things, nothing terrible is going to happen. At least, when as I said, I go back to my students, I say, okay, just do it for just change this tolerance a couple of times and just check physically what you're computing is converging to something. You might not know what the error is, but is it converging to something? It gives you some assurance that
There's a truth that unless your null hypothesis, which in this case would be a Gaussian process, unless it is true, then the more data you have, the easier it is to reject. And eventually you will asymptotically find out that the true thing wasn't a Gaussian process. So we could throw asymptotics at it, and every time we would find out that, lo and behold, what we had was wrong.
I would argue that
But we already know.
it's not, you won't always find that out, because actually one of the things that we've seen in classical numerical analysis is that when people do asymptotics to test for the error here, they end up hitting the error here. And this is a really interesting trade-off in classical numerical analysis. And it shows up a lot in statistics with that numerically unstable formula for computing variance. So when I saw a PhD thesis where Gene Golub was father of matrix computation, or wrote the book on matrix computations with Charlie Van Loon. The guy put up the formula for covariance matrix that was like sum of the outer products plus the outer product of the sum, or sorry, minus the outer product of the sum, sorry, minus the sum of outer product of the sums, right? The bad one. and Gene said, you have a numerically offensive formula on your slide. and so part of the reason that we will do this numerically is to make sure that we're not running into this somewhere in the algorithm.
Any numerical method comes with tweaks, bells, and whistles. It should, when you change them, somehow make the situation better, make your approximation or your representation better. It's that sense of being better, I think, that we're testing. I guess you're saying you don't care about that.
No, we think of better as it does well out of sample, or it's going to be useful for what we're going to use it for. So if we're going to do something with prediction of 10,000 points to get an average, we'll repeat that lots of times numerically to check that it's but we won't, I don't think, I mean, Serge, you fit Gaussian processes. Did you ever think the underlying function actually was a Gaussian process?
No, I like the word fit for purpose, yes. The asymptotics or the validation should be fit for purpose. Is it really asymptotics that we're looking for?
Often the asymptotics don't tell us an awful lot. But if I had an infinite number of data points, my uncertainty would go to 0. Well, that doesn't tell me a lot.
So
Error would know.
I would argue that it tells you a lot if you are reporting this error, but the person that you're reporting it to interprets it as this error. And that's what I think a big part of the problem is in using Gaussian processes for computer experiments, which at least in the case when they're modeling physical things, when there's physics involved. When you say, here's my posterior variance, and I recognize this is a straw man based on regression, but you understand the analogy that you're reporting posterior variance, but it gets interpreted like this. I remember that at that statistical perspectives on UQ meeting, I said something like this to Michael Stein, and Michael Stein said, well, no one really thinks this is the error. And I was like, not from everything that I've heard. that when you report this, even though it's computed as under these assumptions of coming from a Gaussian kernel, Gaussian process, but people interpret it like this, and you make, I don't know, IPCC reports based on this or something, like any kind of like real decision, misinterpreting this as this, I think that can cause real problems.
I agree with that.
Okay.
Yeah, I don't really have any problem with that.
And I think the physicists think that this is the case more so than this being the case. That's my hunch, at least from the physicists that I've worked with. That they believe if they enrich their experiment, then they will get a more accurate number. You feel like we made progress?
Yes.
Good. Should I turn it off? Stop recording.